sort of the granddaddy of all the momentum and energy questions as it be, because there's three things going on. There's a collision, there's conservation of momentum implied in the collision, there's conservation of energy, and there's angles. So there's two dimensions. So this is as big as I can give you, okay? I can't do any more than this. So let's look at the problem first, and then I'll sort of explain my schematic. But I say I've got car A traveling west at 110 kilometers per hour, and car B of a smaller mass runs a stoplight heading north and runs into A. This is my ultimate fear. Whenever I'm driving on the highway, I'm always terrified someone's going to run through their stop sign and run into me head on, right? Or side on, not head on. I've sort of had a couple friends who've had that happen to them. Unfortunately, no one's been hurt too serious, but it happens, right? So anyway, people don't see the stoplight. So this is it. And what are we looking for? So we know what we know after the collision, that they slide to a stop, very similar to Miss Hillary's thing. You know, they slide to a stop, but this time it's on an angle because they're going, you know, they're running into each other side on. So they end up moving on an angle. And I want to know how fast was B going when they ran into car A, okay? So in this one, contradicting what I did last time, I could have kept everything in kilometers per hour, but I chose not to for whatever reason when I wrote out this example. But I could have kept in kilometers per hour, but I didn't, okay? So looking at my picture then, here's the before the collision. So before the collision, there's the blue car who's going to run the stoplight. This one's going 110, so speeding a little bit probably. 30.6, especially if you're on Highway 8 or something. Highway 7, you should only be going 80. Anyway, so you're driving this way, 30.6 meters per second west. And car B, we don't know how fast, but they run right through their stoplight. They run into each other, right? And they move off in this direction. And they're same thing as before, like their tires lock, they're stuck together. We know the combined coefficient of friction on their tires on the cement, and we know they travel for 20 meters. Okay, so it's like a three-step problem, and we want to go back to the beginning and say, well, how fast was this car going? Well, we don't have enough information to find that out until we look at figure out how fast they're going immediately after the collision. So this is the conservation of energy piece. Okay, and exactly like Miss Hillary in her accidents, right? So what we know from a kinetic conservation energy point of view is the kinetic energy that they have right before the accident all turns to heat when the tires lock, right? And then I use conservation of momentum from knowing that speed, velocity, to figure out this vehicle's velocity right before, okay? And treat it as a 2D totally inelastic, okay? So first, the conservation of energy. This might throw you off, but in the conservation of energy, like right after the collision, the cars are traveling on this angle, right? You don't need to worry about angles with energy. You just deal with speeds, right? It's a scalar thing, so you don't deal with the 62 degrees, nothing like that. All you say is, okay, we know the combined mass of the two cars is 1900. You know they end up at a stop. The gravitational is nothing. We want to find the speed. Oh, similar to the last example, by the way, I'm going to jump here. I'm jumping up. Call this 1, this 2, and this 3. So we're looking for V2, right? The speed of the combined speed right after. I know I want to find the combined speed just after the collision, which is just at the beginning of their sliding, right? And I know E thermal is that. I know mu K and delta D, all those things, right? So it's pretty straightforward. Kinetic energy becomes heat, so you just rearrange, solve for V2. So we know that right after the collision, these two cars were traveling at 16.57 meters per second. Okay, that much we know now. So we can go back, and I'm going to jump knowing that you're slower than me. Please pause. But looking right here, just saying, okay, so now we know that after the collision, they were traveling at speed, and we know their angle. We can call that a velocity because we know that, you know, from the forensic data, we know that it was traveling 62 degrees north of west after the collision. So we know the angle and we know the speed, and we now want to use conservation of momentum in 2D to figure out this speed right here. Okay. So jumping down to 2. Now here's something to think about, what I've written in the purple here. we only really need to worry about the y direction. We don't need to solve this question twice because we're only looking for that blue car, right? Well, the blue car was only traveling in the y direction. So if we resolve the blue side, we'll find out VB1 and that'll be our answer. Okay? I mean, there's no VB1x. If you look at it right here, we're assuming that this car was traveling due north, I assume. No, due north at the very beginning. So I don't need to worry at all about the initial x velocities. And in fact, that kind of makes you say, well, I guess that means that the speed that the green car was going doesn't matter. Could have been going 5 meters per second, or it could have been going 100 meters per second. And that's true. So just because this guy was speeding doesn't affect the end position of the collision, which is interesting, or at least the end position. It doesn't affect solving. I just lied to you. It does affect how far it goes in that direction, in the west direction. But it doesn't change the impact of the speed of blue. Anyway, so we just do conservation momentum in the y direction. Here's our givens, right? We know V2y. Okay, we know V2 is 16.57. Well, the V2y then will be sine 62 of that, right? Times sine 62, that'd be the y component of that velocity. We know AY is 0, and we know we want to find VB1. Okay, so here's my general equation for conservation of momentum in the y direction. Totally inelastic collision because they stuck together, right? So let's look. AY is 0. It's going due west, so that's just 0. Here I've got my 800 and VB1y, which is what I'm looking for, equals the combined y component of the velocity, so sine 62 times the velocity, times the speed, and the combined mass. So you just work it out, you solve it, you divide, and you get that it was traveling 34.7 or multiplied by 3.6, 125 kilometers per hour, which is definitely a realistic number. And I think it makes sense because that's going so fast, because, I'm going to scroll up here, looking at the accident, it ends up at a 62-degree angle. So it's like this blue car had more momentum than the green car because it ended up sort of, if it was like 20 degrees, that would mean the green car had more momentum, right? Because it moved more in the x direction afterwards, but actually ended up moving more in the y direction afterwards, which said this guy had more momentum. So he had to be going faster and significantly faster, right? Because this guy's heavier too. Okay, so yep, definitely a good answer. Makes sense based on the results that the blue guy's in deep trouble. Okay, that's it, the granddaddy. That's it for the whole unit actually. Time to do some work.